Hello good people, I would like to talk about a nucleophilic substitution reaction. In particular, I would like to explore the SN1 mechanism. What does SN1 stand for? The S stands for substitution, N for nucleophilic, and the number 1 tells us that the rate determining step, the slowest step, is a unimolecular process. In other words, it only involves one molecule. So generally speaking, in a nucleophilic substitution reaction, we have a substrate of some sort with a leaving group, which can in itself be a nucleophile. We have a new nucleophile that comes in, and when everything is said and done, the new nucleophile is on the substrate, and the leaving group, as the name suggests, has left. All well and good. Let's look at an example. So here's a substrate. I have drawn 2-methyl-2-butanol. Note that this is a tertiary alcohol. In other words, the carbon that is bonded to the hydroxy group is also bonded to 3 other carbons. It is a tertiary carbon, and this is a tertiary alcohol. So what will happen? Well, the hydroxide group is a leaving group. However, it is not a particularly good leaving group. How could we turn it into a good leaving group? Well, we could perform this reaction in acidic conditions. If we do that, we will have this species here, protonated water, which is also known as a hydronium ion. The lone pairs of electrons on the oxygen, on the hydroxide, will be attracted to one of these protons. They will grab it, and as a result, we'll end up with this species here. So this here now is an oxonium ion. So it's an oxygen that carries a positive charge. And if you look at this part here, this is H2O. It is water, and water is a very good leaving group. And this is the crux of an SN1 mechanism. We will have a conversion of this oxonium ion to this carbocation here. And that is the rate determining step. That is the slow step, the formation of the carbocation. Note that this is a tertiary carbocation. The carbon that carries the positive charge is bonded to 3 other carbons. Please recall that tertiary carbocations are more stable than secondary carbocations, which in turn are more stable than primary carbocations. That means that tertiary alcohols or tertiary carbons will be more susceptible to an SN1 mechanism because they lead to a stable tertiary carbocation. Fair enough. What will happen next here in our reaction? Well, now that we have this carbocation, we can introduce our nucleophile. I have chosen methanol. The lone pair electrons of this oxygen will be attracted to the positive charge of the carbocation. And once again, we will end up with an oxonium ion. So an oxygen that has 3 bonds. And now we will get a deprotonation step. A water molecule will come in, and the the electrons on the oxygen will be attracted to this proton here. And finally, we will end up with our product. In this particular case, it's an ether, 2-methoxy-2-methylbutane. And please note that the water has grabbed the hydrogen, and as a result, we have a hydronium ion again. So you could argue that this hydronium ion is now free to go back to the start and react with another molecule of 2-methyl-2-butanol, our starting material, our substrate, and the whole process can start again. So the key thing in an SN1 mechanism is that you need to form a carbocation. And because tertiary carbocations are more stable, a substrate that will lead to a tertiary carbocation will be more susceptible to an SN1 mechanism than a substrate that leads to a secondary carbocation or a primary carbocation. That is all for now, and I will see you on the flip side.